Good afternoon, everyone. Uh, let's start the class for the course code CSB 1213 ordinary differential equations. Today we'll be starting uh, our first block in differential equation. And in first block, it consists of unit 1, unit 2, and unit 3, unit 4. So in unit 1, degree order solution of a DE and formation of a differential equation. Unit 2, differential equation of the first order, first degree separation of variable method, solution of homogeneous equation, linear differential equation and Bernoulli equation. Unit 4, exact differential equation. Let's see how much we can cover within the time period from the block 1. So moving to the block 1, unit 1, degree order solution of a DE differential equation and formation of a differential equation. So here we'll see the convergence sequence, formation of differential equations. So first, let us first discuss in the introduction. The differential equation is an equation that involves one or more derivatives of an unknown function. It describes how a function changes based on its rate of change or its relationship with other variables. So, in differential equations are widely used in various fields, including physics, engineering, biology, economic, and more. So, next is the degree of differential equation is the highest order of the derivative present in the equation. For example, if the highest derivative of the unknown function in an equation is the second derivative, it's called a second degree differential equation. So the order of a differential equation is the highest derivatives that appear in the equation regardless of their power. So finding a solution to a differential equation means determining the function or set of function that satisfy the equation. So some important definitions we'll be seeing here is differential equation. Suppose that y equal to fx is a function in which x is independent variable and y is dependent variable. A differential equation is an equation which involves various differential coefficient or differential of dependent variable with respect independent variable. Here we'll see some example. dy by dx equal to x log x, dy equal to cos x dx. And next is the derivative of second derivative is d squared y by dx squared. So here minus 4 by dy dx minus 12y equal to, what's the solution here? If we put the dy dx value 5e to the power x plus sine x plus x cube. So ordinary differential equation. Next is ordinary differential equation. An ordinary differential equation is that which involve only one independent variable and differential coefficient with respect to it. The above example are of this type. The above example is of ordinary differential equation. So next, moving to the next definition is order of a differential equation. The order of a differential equation is the order of the highest differential coefficient which appear in it. Example, the differential equation d square y by dx square plus 4y equal to e to the power x is of second order. Degree of, next, moving to the next definition. Degree of a differential equation. The degree of a differential equation is the degree of the highest differential coefficient which appear in it. Uh, when the differential coefficient are free from radicals and fractional powers, then we can say it's a degree of differentialism. The example given here is 1 plus, in the third bracket, 1 plus bracket dy dx close the third bracket to the power 4 equal to a square, second derivative d square y by dx square to the power q is of degree 3. The degree of d square y by dx square. Example, find the order. Let's see the example now. Find the order to for the better understanding and find the order and degree of the differential equation. So here there's a given example 1, 2, then solution. For the first example, y, here is the derivative dy by dx equal to a to the root 1 plus cy dx to the power 2. So squaring to get rid of radicals, y minus x dy by dx square equal to a square within bracket 1 plus dy dx square. So this is how we get rid of radicals. Then which is the first order and second order. So the highest degree of dy dx is 2 based on the power of this equation. So here next example 1 plus dy dx square 3 by 2. Then here you see a, if a is coming in front, then this d square y dx square, squaring to get rid of radicals. Now we'll do squaring, then radicals will be removed, then a square again, this square will come here, there's 3, which is the second order and second degree. Because here the degree is 2. Next is solution of a differential equation. The solution of a differential equation is the functional relation between the variable involved which satisfy the equation. So general. Next, any doubts so far? Okay. If there is no doubt, let's move to general solution. The solution of a differential equation in which the number of arbitrary constant is equal to the order of the differential equation is called the general solution, or complete solution, or complete integral, or complete primitive. So these are the few different names for this general solution. And next, particular solution. If particular values are given to the arbitrary constant, then in the general solution, then the solution obtained is called a particular solution. Singular solution. A solution which does not contain any arbitrary constant. Then and also it's not obtainable from the general solution by giving particular values to the arbitrary constant is called singular solution. Example, here are a few examples. See, you go through it, this example, for the better understanding. So if we see, for example, to verify that y equal to within bracket x cube minus x log cs satisfy the differential equation. Now we have to check whether y equal to this satisfy the differential equation. X cube minus x within bracket x this minus 3x square minus 1 within bracket y equal to x to the power 5 minus twice x cube plus x. This for all value of c. So this is the equation which we have to verify whether it satisfies the differential equation. The given differential equation is this one. We have put the equation 1. The given function is this one. So differentiating with respect to x. So here we have put the values. See? Then substituting the values of y and y dash in equation 1. So we'll substitute the value of y and y dash in equation 1. Then we get equal to x to the power 5 minus twice x cube plus x equal to x cube then minus twice x plus x. So this is this satisfies this equation. So which is identically true. Since the given function satisfy one, it is the solution of equation 1. So formation of differential equation. Rule to form the differential equation. Excuse me. Rule to form the differential equation from a given equation is x and y containing arbitrary constant. So write down the given equation. Differentiate with respect to x successively as many times as the number of arbitrary constant. So eliminate the arbitrary constant from the equation of the above two steps. So these are the rules to form the differential equation from a given equation. So the resulting equation is the required differential equation. These are more example for you to practice. So go through it. And we conclude the unit 1 from block 1. Now going forward to unit 2. Differential equation of the first order of the first degree separation of variable method. Solution of homogeneous equation. So here we'll see the separation of variable method, homogeneous function, homogeneous differential equation, and exercises. Now, before going forward to further understanding, let's see the introduction part. We have seen the first order, first degree. Here we'll see more in detail. Differential equation of the first order and first degree are fundamental in mathematics and find widespread application in the various fields. These equations This equation involves the first derivative of an unknown function with respect to a single independent variable. So the first order, first degree differential equation, let us know about it. This equation is expressed as dy by dx equal to f within bracket x comma y, where y is the unknown function of x and its derivative. The function fxy relates the rate of change of y to its current value and the independent variable x. So remember this. And separation of variable method. The separation of variable method is a powerful technique used to solve first order differential equation. So Here we can see after separation, integration is applied to both the sides to solve for y. Next is the solution of homogeneous equation. How to find the solution of the homogeneous equation? Homogeneous first order differential equation are those that can be represented in the form dy dx equal to f y by x or m xy dx plus n xy dy equal to 0. This is the equation where f is the function of the ratio xy or m and n are homogeneous function of the same degree. If it is the same degree, then we can say it's a homogeneous function. Moving next, example, solve dy dx equal to 1 plus x y cube by 1 plus x square. Sorry, x y square by 1 plus x square. Solution we have is again separating the variables we get. Now we will separate dy again dy. Dx will cross the dy and dx. Na? Sorry, y value in one side, x value in one side. So dy by 1 plus x y square equal to dx by 1 plus x square. Integrating both sides, we get 10 to the power minus 1 y equal 10 to the power minus 1 x plus 10 to the power minus 1 c. C is constant, where 10 to the power 1 c is an arbitrary constant of integration. So now breaking the equation, you see x value equal to constant, then we choose the common here, then this is the value and equal to c 1 plus x1, which is the required solution. So this is how the solution for separations of variable method work. So there are more few example here which you can practice at home. For the homogeneous function, again we have already explained, again we will explain more about it. The function in which every term is of the same degree. Same degree is known as homogeneous function of that degree. For example, let fx equal to a0 x to the power n plus a1 x to the power n minus 1. So that's this to be equation 1 be a function of x and y. We see that every term of this function has the same degree, that is n. Now equation 1 can be rewritten as function f x comma y x to the power n, and this one we have rewritten here. There's every homogeneous function of x and y of a degree. Here you see the final equation is equal to x to the power n f y by x. Degree n can be put in the form of this. Okay, for today's class, I think we'll do only till unit 2, because since there are too much of example here, you can practice at home. You see there are unit and unit exercise also given. You can practice at home as much as possible. And for the next class, we'll start from unit 3 from block 1. Thank you for the class. See you in the next class.